Hello everyone. Welcome to the class of Discrete Mathematical Structures. Today, I'll be teaching a topic in Module 1, Fundamentals of Logic, and the topic name is Logical Implication Involving Quantifiers. Myself, Dr. Madhura, Assistant Professor, Department of Mathematics, Sai Vidya Institute of Technology, Bengaluru. Logical implication. A quantified statement P is said to logically imply a quantified statement Q if Q is true whenever P is true, and then we write the expression P implies Q. We have learned the implication in the compound propositions. So in that, we had learned about the logical equivalence, logical implication definition. The same is applicable here also. So we have a quantified statement P here, and we say that P is logically implying Q, another quantified statement Q, if Q is true whenever P is true. So whenever P is true, he must have Q to be true. Then we can write down P implies Q. Note, given a set of quantified statements P1, P2, P3, etc. up to Pn, and another quantified statement say Q, we say that Q is a valid conclusion from the premises P1, P2, P3, etc. up to Pn, or P1 and P2 and P3 and etc. up to Pn, conditional Q is a valid argument if Q is true whenever each of P1, P2, P3 up to Pn is true. Or equivalently, we can write down the expression P1 and P2 and P3 etc. up to Pn implies Q. So we understand this note. We have a set of quantified statements P1 to Pn and other quantified statement Q. And we say that Q is a valid conclusion. It gives a valid conclusion from the premises P1, P2, P3 to Pn, or it is one and the same as reading P1 and P2 and P3 etc. up to Pn. Conditional Q is a valid argument. And this can happen whenever each of P1 to Pn is true, Q must be true. The same is symbolically written as P1 and P2 and P3 etc. up to and Pn implies Q. So this is all about logical implication. So we can work out problems on logical implication. Problems on logical implication using quantifiers. We'll take up the first question. Before I go on to the question, I'll give a common heading for all the problems. For each of the following, determine whether the following arguments are valid or not. So for each of the following, we have to determine whether the following arguments are valid or not. Right, in that first question, for the universe of set of all students, no engineering student is bad in studies. No engineering student is bad in studies. Next sentence you can write down. Anil is not bad in studies. Anil is not bad in studies. And the conclusion is, therefore, Anil is an engineering student. Anil is an engineering student. So very firstly, we have to denote the open statements P of x, Q of x, etc. And there is a element here. The element A is here, Anil. The student name is Anil here. So we denote the student name A as Anil. And the open statements P of x and Q of x also can be defined. So let us see the solution. Let us denote P of x by X is an engineering student. X is an engineering student. And let us denote Q of X as X is not bad in studies. X is not bad in studies. We take the variable X here because they are in general talking about no engineering student is bad in studies. So it comes to the set of all students here. The universe is nothing but the set of all students. So that is why we talk in general in terms of X, the variable X. And in that, a particular student is taken into consideration, that is about Anil. So we will denote the student name Anil by the element A. The element A. So that now the given argument reads, given argument reads. Now it is very important to write down the given argument. So very firstly, when we look into the statement, we cannot have any logical connective in general. We cannot observe any logical connective. But we can put the first statement in alternate manner also. We have the statement as no engineering student is bad in studies. No engineering student is bad in studies, they have given. And this can be written in other form as, if X is an engineering student, then X is not bad in studies. We can alternately call the first sentence in the form of if then. That is implication or the conditional form we will be able to represent. So if X is an engineering student, then he is not bad in studies. X is not bad in studies. So if then form, we can understand the first statement. So it can be written in symbolical form as, for every X, P of X conditional Q of X. P of X conditional Q of X. So if P then Q. If P then Q means if X is an engineering student, then X is not bad in studies. Is same as reading no engineering student is bad in studies. So this is for the first statement in the form of if and then. Now the second one says Anil is not bad in studies. Any particular student X is not bad in studies is denoted by Q of X. But here now we are talking about Anil. So Anil is not bad in studies can be represented as Q of A. Q of A. Now we have the conclusion. So therefore, the conclusion is Anil is an engineering student. So X is an engineering student means Anil in particular we are talking about. So it is P of A. P of A. Because P of X is represented with respect to any engineering student. X is an engineering student. In particular, we are talking about Anil is an engineering student. So it can be symbolically written as P of A. Now, we need to check whether this argument is a valid argument or an invalid argument. So in order to check whether this is valid or invalid, we take and between the premises as we did in the compound propositions previously. So we take and between the premises and try to get the conclusion. If we arrive at the conclusion, then given argument is valid, otherwise it is invalid. So let us consider for every x, p of x conditional q of x and q of a we have. So we have this expression. Now this can imply, this is true for every x. P of x conditional q of x is true for every x. So I can apply it for Anil also. I can apply for the element or the student Anil also. So this can be symbolically written as P of a conditional q of a. P of a conditional q of a and q of a. P of a conditional q of a. It is valid for the student Anil also. Anil is represented by the element a. So for every x, this is a valid statement. So we can imply for Anil also. So P of a conditional q of a and q of a we have. Now, does this imply P of a? No, it does not imply P of a. Why it does not imply P of a? Right, it is not giving us by applying any of the rules of inferences what we learned. So Modus-Pon's rule says that P conditional Q and P is Q. Modus-Pon's rule says that P conditional Q and P implies Q. Whereas if we have P conditional Q and Q, it does not imply P. So we cannot apply Modus-Pon's rules also to get the required thing. So we are not able to arrive at P of A. So what is the conclusion? Given argument is not valid. So we will conclude and write on the words. Thus, given argument is not valid. Given argument is not valid. So that was about the first problem. So we had to verify whether each of these determine a valid argument or an invalid argument. Second one, no engineering student of first or second semester studies logic. Second sentence, Anil is an engineering student. Anil is an engineering student who studies logic. Therefore, Anil is not in second semester. Therefore, Anil is not in second semester. So this is our question. So let us do the solution. It is similar to the previous one, but there is a small change here. Here also we are considering the set of all students as the universe. Though it is not mentioned, we can assume it. So here we have engineering students as a set of all students, that is engineering students as the universe here. Right? So we will have to consider the set of all engineering students as the universe, and P of x and Q of x is with respect to first semester and second semester. And we can assume another proposition or another open statement in the form R of x, wherein x studies logic. Right? And the element A here is Anil. The element A here also is Anil. So let us do the solution part. Let the universe be the set of all engineering students Let the universe be the set of all engineering students. And let us assume P of X as X is in first semester, X is in first semester, and let us assume Q of X as X is in second semester. X is in second semester. So it says either first semester or second semester. So or logical connective can be used here. And no engineering students studies, who is in first or second semester studies logic, it seems. So we can assume R of X as X studies logic. So R of X, let us assume X studies logic. And we have the element A, that is Anil. Anil. So with all these, we are now able to write down the given argument. Given argument reads, given argument can be read as, for every x, P of X or Q of X, P of X or Q of X, conditional negation R of X is the first statement. Let me make you understand how is this. So we have the given argument for every X, because we are talking about every engineering student. And they say that every engineering student is either in the first or second semester. So X is in first semester or X is in second semester. Or, so P of X or Q of X. And the first statement can be alternately put in the form that if every engineering student of first or second semester, then they do not study logics. If then form, we can put it in the if then form, no? If every engineering student is of first or second semester, then they do not study logic. So do not study logic is negation R of X. X studies logic is denoted by R of X. They do not study logic is denoted by negation R of X. So very first statement is actually put in the form of if then form. So P of X or Q of X, conditional negation R of X. Second statement says Anil is an engineering student who studies logic. Studying logic is R of X, and they are talking about a particular student, Anil. So we can represent the second one as R of A. R of A. And the conclusion is, therefore, we have Anil is not in second semester. Anil is, with respect to the element, is not in second semester. So this can be written symbolically as Q of A. Not in second semester, so negation Q of A. Negation Q of A. If Anil was in second semester, it would have been represented as Q of A, but he is not in second semester is the conclusion, so negation Q of A. Now again, as usual, we take and between the premises and try to arrive at the conclusion. If we arrive at the conclusion, then the given argument is valid, otherwise it is invalid. So let us consider for every x, P of X or Q of X, conditional negation R of X and R of A. We consider this. We consider the expression, whatever we have between the premises, and we consider and do. Since we have the first expression with respect to every x, so for every x, this is a valid statement. So for Anil also, this is valid. So we can take in place of x, a for a particular element and rewrite the expression. So this implies for us P of A or Q of A, conditional negation R of A. Conditional negation R of A and R of A. And R of A. Now we need to simplify this compound proposition or the open statement that we have here, and we need to arrive at negation Q of A. So let's see whether we can arrive at the same thing. Now, I rearrange this expression. There is and between these two compound propositions. So I will just apply commutative law first and take this R of A to the left part and this P of A or Q of A conditional negation R of A to the after and symbol. So we have R of A and P of A or Q of A conditional negation R of A. So here I have just applied commutative law. I have applied commutative law and obtained this. And we remember contrapositive, no? For any conditional P conditional Q, what is the contrapositive of P conditional Q? It is negation Q conditional negation P. So let us apply contrapositive for this conditional what we are seeing here. Okay, so we have a conditional expression here, P of A or Q of A, conditional negation R of A. We take the contrapositive of this and write down. So this is giving us R of A and the contrapositive of this is R of A conditional P of A. It is actually negation of P of A or Q of A. Right, so there's a negation here. Hope you can see that. So we applied here actually contrapositive. Contrapositive. I just highlighted the negation so that you all can clearly see it. So we have it now in the form P and P conditional Q. So according to rule of modus pons, what is P and P conditional Q? P and P conditional Q is nothing but Q. So let me write that whatever I am applying in capital P form so that it will clear for you. This is P and P conditional Q. P and P conditional Q implies Q. Q. This is using actually modus pons. Rule of modus pons. Right. So keeping this in mind, we have to arrive at Q now. So let us write down the expression what is Q and put it below the logical equivalence. Next symbol, this implies Q. Q is negation of P of A or Q of A. Negation of P of A or Q of A. I repeat once again, R of A is P, R of A is P. Conditional, this entire negation of P of A or Q of A I have taken as Q for convenient. So this was of the form P and P conditional Q. P and P conditional Q implies Q by the rule of modus pons. So we have to write down just the Q expression. So Q expression is negation of P of A or Q of A. So I have written the same thing. Now we apply De Morgan's law and rewrite this expression. So by applying De Morgan's law, this is negation P of A and negation Q of A. Negation P of A and negation Q of A, we applied De Morgan's law. Is that our requirement? No, our requirement is negation of Q of A. So we have it in the form P and Q. We have this expression in the form P and Q. By the rule of conjunctive simplification, P and Q gives us P. P and Q also implies Q or it can imply P. So we are applying the rule of conjunctive simplification. I'll just write down the next one. So this implies for us negation Q of A. And this is by the rule, which rule we applied? Rule of conjunctive simplification. That is, P and Q implies P. P and Q also implies Q. So we can now use commutative law and actually rewrite this now. So we had the expression negation P of A and negation Q of A. So we can take P and Q as Q and P by applying commutative law also. Correct? So we can apply that as well and obtain the resultant. So we have applying De Morgan's law, you can actually put implies and implies by symbol. That is nothing but logical equivalence symbol, where we applied De Morgan's law, and where we applied contrapositive also you can apply and implies by symbol. That is logical equivalence symbol. So for all the laws of logic, we'll be applying logical equivalence symbol, and for rules of inference, we'll be writing implies symbol. We recall that from the previous topic. So we have arrived at the required thing, that is negation Q of A was our resultant. So hence we will be able to conclude that the given argument is a valid argument. So let us write down the conclusion. Therefore, given argument is valid. We'll see the third problem. For every x, P of x conditional Q of x, for every x, Q of x conditional R of x. Therefore, for every x, P of x conditional R of x. So this is the required argument. Here the argument is not given in the form of a statement problem. It is directly mentioned with respect to the open statements PQR, P of x, Q of x and R of x. X is the universal set here. So x is the element in the universal set. Okay. So let us see the solution. Solution for the same. Let S be the universe and A be any element in the universe S. So that is the very first assumption that we do. We cannot keep it with in general in terms of the variable x and do. We have to take a particular element in the universe and we have to do. So let S be the universe and A be one of the element in the universe S. Now we will write down the given premises in the form of and. So we have for every x, P of x conditional Q of x, and for every x, Q of x conditional R of x. So these are the given premises for us. Now there is a this is valid for every x, so we can apply it for the element A also, which belongs to the universe. So this implies P of A conditional Q of A and Q of A conditional R of A. This is actually by the rule of universal specification. Hope you recall the rule of universal specification is applicable for every element x, means we can take it for the element A also. So we can just write down the reason here. So this is by the rule of universal specification. Universal specification. Now this is of the form P conditional Q and Q conditional R. By the rule of syllogism, we can write it down as P of A conditional R of A. Rule of syllogism says that P conditional Q and Q conditional R implies P conditional R. So we applied here rule of syllogism. Rule of syllogism. Now this can be rewritten as for every x, p of x conditional r of x. This is from the rule of universal generalization. We recall the rule of universal generalization. If for any element A, it is applicable, that is P of A conditional R of A, then we can generalize it for using the rule of universal generalization and write it down for every X, P of X conditional R of X. So this is by the rule of universal generalization. Rule of universal generalization. So we have arrived at the required conclusion, that is for every x, p of x conditional r of x we have arrived at. So we can conclude the given argument is valid. So it was not a statement problem. Directly the open statements were mentioned for us and we had to apply the rules of inferences and obtain the given resultant, and we obtain that it is a given argument is a valid statement. We'll see the next problem, fourth one. Fourth one, for every x, p of x or q of x, for some x, negation p of x, for every x, negation q of x or r of x, negation q of x or r of x, and the fourth statement is for every x, s of x, conditional negation r of x. And the conclusion, therefore, for some x, negation s of x is the conclusion. So we have to verify whether this is a valid argument or not. So let us take the solution. Let us assume S be the universe and A is any element in the universe. A belongs to S. We will take AND between the premises and try to prove the resultant. So I will take AND between the premises first. For every x, p of x or q of x, and for some x, negation p of x, and for every x, negation q of x or r of x, and for every x, s of x, conditional negation r of x. So these are the given premises and I've taken and between them. So just to recognize step by step, I will just use a different ink and write down for your convenient. So this is valid for every x. So we'll assume that it is valid for the element A also. The second premises is for some x, negation p of x. So for some x, this is a valid argument, valid statement. So that some x we are assuming as the element A itself. So element A is satisfying for some x as well as for every x. So we are assuming the element A itself is that element which is satisfying the proposition which is of the form for some x also. Okay, so let us write down the next step. So this implies P of A or Q of A, P of A or Q of A, and negation P of A, negation P of A, and negation Q of A or R of A, and S of A conditional negation R of A. S of A conditional negation R of A. So this is the given premises with respect to the element A. Now we observe the first two terms. The first two terms, right, is of the form P or Q and negation P, right? P or Q and negation P. P or Q and negation P implies Q by the rule of disjunctive syllogism. So I'll just represent the same thing first and show it to you here. So this is of the form P or Q and negation P. P or Q and negation P implies Q. And this is by the rule of disjunctive syllogism. By the rule of disjunctive syllogism. So using this rule for the first two terms here, we will be able to write on the next step. So next step will imply for us just Q. Just Q means I should write down Q of A. Q of E. Remaining I am writing as it is. So and negation Q of A or R of A and S of A conditional negation R of A. S of A conditional negation R of A. Now again we observe the second of the two terms over here. So we observe this first and the second term here. So again it is of the form P or Q and negation P. It is of the same format now. So I'll just mark that for you. So this is of the form P or Q and negation P. P or Q and negation P. This will again imply Q by the rule of disjunctive syllogism. Again by the rule of disjunctive syllogism, this is of the form P, the first two terms I'm talking about. It is of the form P or Q and negation P. So will imply us Q to us. What is Q here? Q is just R of A term. So we will write down R of A. So we'll just write down this as R of A because this is implying Q for us. So R of A, and the last term I will write as it is S of A conditional negation R of A. S of A conditional negation R of A I have written as it is. Now this by the rule of modus tollens. What is modus tollens? P conditional Q and negation Q implies negation P. So we are applying the rule of modus tollens to arrive at the next step. So I will just write the rule what we are applying. This is of the form P conditional Q and negation Q will imply us negation P. Negation P for us. So this is by the rule of modus tollens. Rule of modus tollens. We will apply this step to the next one. So we have P conditional Q and negation Q, and this should imply as negation P. So negation P means it will become negation S of A. On comparison, this becomes negation S of A. Negation S of A. So we can now write it down for some X. This implies as for some X, this is negation S of X. Negation S of X. So how we will be able to write down in that form is, we saw in the previous problem that we can apply, if it is applicable for some element X, we are applying if it is applicable for some element A, then we can apply it for the element X. It is the rule of universal generalization. Universal generalization. So applying that, we are able to write on. And we took for some X because it was for some X negation P of X in one of the premises. And for some X, we have taken as the element A itself. So that is the reason we can write down for some X negation S of X. So we have arrived at the required expression for us, the required conclusion, whatever was given, we have arrived at that. So we can now conclude that given argument is valid. So this was the fourth problem to you. We'll see the fifth problem. Fifth one. For every X, P of X or Q of X. Second statement. For every X, negation P of X and Q of X. We'll put a separate bracket for this. Conditional R of X. And therefore, conclusion is for every X, negation R of X, conditional P of X. Conditional P of X. So we have to arrive at the given conclusion. If we arrive at the given conclusion, then the given argument is valid, otherwise it is invalid. So let us see the solution. So first we will assume S be the universe. S be the universe and A be any element in the universe. A be any element in the universe. So we will take AND between the premises first and try to arrive at the required thing. For every X, P of X or Q of X, and for every X, negation P of X and Q of X, conditional R of X. So this is the given premises. We have taken AND between them. This is valid for every X, so we can apply it for the element A also and rewrite the expression. So we have P of A or Q of A and negation P of A, negation P of A and Q of A, conditional R of A. Conditional R of A. So we have this expression P or Q form. P or Q using implication can be written as negation P conditional Q. So P conditional Q is equivalent to negation P or Q. So same thing is applicable vice versa. So we have it in the form P or Q. This is same as writing negation P conditional Q. And we have the second one in the form of conditional. We remove the conditional. So write it down in the form of OR. So for both of these, we are using the same formula, but in the reverse way we are using it. So what I mean to say is, for the first one, we are using P or Q is logically equivalent to negation P conditional Q. And for the second one, it is already of the form P conditional Q. And this we write it down as negation P or Q. So both these we are applying the formula and we will write down the next step with that. So this implies the first element gives us negation P of A conditional Q of A. Negation P of A conditional Q of A, and P conditional Q should be now written as negation P or Q. So negation P of A and Q of A or R of A or R of A. So this was both application of P conditional Q formula for us. So here we will write down logically equivalent to, because we are applying one of the laws in the that we learned in the laws of logic. Okay. So next step, we can use De Morgan's law. We can apply De Morgan's law, and we can use negation P of A and Q of A. Can be written as P of A or negation Q of A. So it's an application of De Morgan's law in the next step. So negation P of A, conditional Q of A, I will write down as it is. And this gives us P of A or negation Q of A or R of A. So here we applied De Morgan's law. So I'll just quote that for you. De Morgan's law. Now, in the next step, we will just reverse or exchange the brackets and apply. It's an application of associative law for us. We will we have arranging the brackets here. Since both are or in the second bracket, P of A or negation Q of A or R of A we are just exchanging the brackets. We will put it P of A or R of A together in a single bracket and write down the expression. Okay. So it's an application of associative law, what I am doing. So we have negation P of A, conditional Q of A. I will write this as it is first. And negation Q of A, we will write down separately, or in a separate bracket, we will write down P of A or R of A. So this was an application of De Morgan's law for us. I'm sorry, associative law for us. Associative law. So what is the help of writing down or applying that associative law is, next step we can apply again, it is of the form P or Q, no? This is of the form P or Q. So what did we write down in the form of implication? P or Q is logically equivalent to negation P conditional. So this will now get Q of A conditional P of A or Q of A. We'll be able to write down again in the form of conditional. Okay. So we will just apply that step. Negation P of A, conditional Q of A. I'll write down as it is. And this gives me in the form of conditional that it is Q of A conditional P of A or R of A. Right? So this was an application. What formula we use, I'll just write down here. So we had it in the form P or Q. P or Q is logically equivalent to negation P conditional Q. P or Q form we had it. P or Q form we had it. P or Q is logically equivalent to negation P conditional Q. So negation Q of A becomes Q of A, law of double negation. We can directly write down conditional Q, whatever we had, I have written as this. Right? So what does this help me to do now? You have rule of syllogism to apply in the next step. So it is of the form P conditional Q and Q conditional R. So P conditional Q and Q conditional R gives us P conditional R, which is nothing but the rule of syllogism for us. So I will write down, apply that rule of syllogism. So it is negation P of A conditional P of A or R of A. P of A or R of A. And the rule we have used is rule of syllogism. Rule of syllogism. Now, again, we have it in the form P conditional Q. We again have it in the form P conditional Q. So this is logically equivalent to negation P or Q. So again, we apply that P conditional form and apply the next step. We can write down. So this becomes logically implies as negation P or Q form I have to write down. So negation P becomes P of A or Q. Q is nothing but P of A or R of A. Again, by the concept of associative law, I can just exchange the brackets, right? We can just exchange the brackets because both are or. We can exchange the brackets and write it down as P of A or P of A together in one bracket or R of A separately. So this is helping me that we are applying associative law. Associative law for us. So what was the help of doing associative law? P or P is nothing but P itself. P or P can be just written as P itself. So this gives us P of A or R of A. P of A or R of A. P of A or R of A again in the form of or we have, and this can be rewritten as again in the form of R, whatever we have can be converted to conditional using the formula P or Q is logically equivalent to negation P conditional Q. So negation P conditional Q means I can write it down as negation P of A conditional R of A. Negation P of A conditional R of A. Now using contrapositive, how can we write it down? This can be rewritten as using contrapositive. This is negation R of A conditional P of A. Using the concept of contrapositive. Contrapositive. And of course, in the previous step, I used the formula P or Q. P or Q is logically equivalent to negation P conditional Q. Negation P conditional Q I used here, previous step. This step I have used contrapositive. P conditional Q contrapositive is negation Q conditional negation P. Have you arrived at the required thing? This is for every x negation R of x conditional P of x. We have it for the element A now. So we will be able to conclude that it is valid for negation R of A conditional negation P of A. Negation R of A conditional P of A can be now written for every x negation R of x conditional P of x. So therefore, I'll just put that conclusion in the next page. So therefore, we will be able to write down for every x, we have negation R of x conditional P of x. So since we have arrived at the required thing, we can conclude given argument is valid. So thus we are concluding we are given argument is valid. So this was the fifth problem and the last problem which I wanted to consider in the topic what I did, that is logical implication involving quantifiers. So that's all for today. Thank you for watching.